Where does the idea of energy come from? Let's start with kinematics. And to begin, let's start with one-dimensional kinematics with constant acceleration. In that case, you have these two formulas saying where something is and how fast it's going. These two formulas can be combined to give this other kinematics formula. V squared equals V0 squared plus 2a delta x. Now we can multiply this equation by 1/2 m and something interesting happens. We get 1/2 mv squared equals 1/2 mv0 squared plus ma times delta x. This expression, 1/2 mv squared, we call kinetic energy. We give it symbol k. Some books will say ke, others will say t. I'm going to use k here. So this is saying the kinetic energy k equals the initial kinetic energy, k0, plus ma times delta x. So k minus k0 is delta k. And the ma, we've seen that before, it's the sum of the forces. Now, you might be wondering, well, that's in one dimension. What about if we're moving in two dimensions? Well, the exact same argument works. 1/2 mvx squared is 1/2 mv0x squared plus sum of forces in the x, delta x, and 1/2 mvy squared likewise. If you add these two equations together, vx squared plus vy squared is v squared. So you get 1/2 mv squared equals 1/2 mv0 squared plus, and if you do force x delta x plus force y delta y, that's a dot product. You're doing the dot product of the sum of the forces times the displacement in two dimensions. And so this formula is not just one-dimensional, it's very general. All right, what good is it? Why do we care about kinetic energy? Well, it's a shortcut. Energy is what we call a conserved quantity. And conserved quantities are shortcuts. They're nice, easy formulas. Conservation of energy, conservation of momentum, conservation of angular momentum, conservation of mass for that matter. These all make physics easier to do. When you're in doubt as to what to try on a physics problem, try energy. So we have this kinetic energy, starting kinetic energy, and this quantity, which we actually call work. Here's the interesting bit. For some forces, not all, you can write a formula that will figure out all of the work done just by knowing the starting position and the ending position. And this is called a potential energy function. For gravity, the force is down mg, the potential energy formula is mgh. For the force of a spring, minus k delta x, it turns out the potential energy is 1/2 k delta x squared. And if I used some calculus, I could show you what we're doing here. That force is negative derivative potential energy. But if you don't know calculus, never mind that. The force of friction does not have a potential energy formula. It's not what we call conservative. Because saying where you started and where you ended is not enough information to find out how much work friction did. Because if you did like 20 laps, that's a whole lot more work done by friction. That's a whole lot more energy lost to the surroundings. So there isn't any formula that goes from beginning position to end position and that's it. Which means that these forces can be split up into ones that are conservative and ones that are not. The change in kinetic energy is the sum of all forces dotted with displacement. And we split it up into the change in kinetic energy is sum of the conservative forces dotted with displacement plus the sum of the non-conservative forces dotted with displacement. Now, work is the name for these things, the work done by conservative force and the work done by non-conservative force. But work done by a conservative force, it is minus the change in U. U is the symbol for potential energy. Some classes might call it PE, potential energy. A lot of books call it U. So it turns out that work is negative change in delta U. So it's negative of U final minus U initial, so it's U initial minus U final. That means that the change in kinetic energy is minus the change in potential energy for all the conservative forces, plus the work done by non-conservative forces. Or delta K plus delta U is the work done by non-conservative forces. And if you don't have any non-conservative forces, like you're in a frictionless environment, this non-conservative work is 0, and then you have the change in kinetic plus change in potential is 0. So energy is constant. And this is extremely useful. this formula can be rearranged into the U initial and K initial plus work done by non-conservative forces is U final plus K final. So potential energy plus kinetic energy is what we call the total energy. And so the energy only changes if you do non-conservative work. Here's one quick example to show what I mean about this being useful. Suppose you're driving up a winding mountain road and you wanted to figure out how much work the engine did. If you were going to figure out the work done by gravity, you would have to say, okay, this displacement and this gravity have dot product, and then this displacement gravity dot product, and then this one, and then this one, and then this one. You'd have this mess of vectors you'd have to work through. But instead of all that, we can simply use conservation of energy and say energy initial plus kinetic energy initial plus work done by non-conservative or outside forces equals U final plus kinetic energy final. If I hit the gas so that the car maintains a speed of 10 meters per second all the way up, then the initial kinetic energy is going to be 1/2 mv squared, and the final kinetic energy is going to be 1/2 mv squared, and they'll actually cancel. The initial potential energy, if I say this is 0 meters, and I can, because we get to choose origin, the initial potential energy is 0. So the work done by non-conservative forces, i.e. the motor, is mgh, 1,000 kilograms, 9.8 meter per second squared, 100 meters. That's 9.8 times 10 to the 5th Newton times meter, or 9.8 times 10 to the 5th joules. Joule is the unit for energy and work. That was a lot easier than working out a whole bunch of dot products.